welcome back from spring break. Hope you enjoyed your break off, your time off, that is. And we kind of finished JDBC before we left for break. I did want to have one final summary of best practices before we talk about what we're going to talk about today, which is one of those bonus or one of those extra lectures that I kind of do in the H section. And we're going to look a very quick introduction to multi-threaded programming. Before we do, though, there is a question online from the YouTube stream about errors logging. Using the logger, and you do need to download log4j if you're going to use it. If you want, I think that was in Thursday's lecture right before the break. I took you through the process of downloading it. There are 2 jars that you need to include. In fact, it's over here. The jars that you need to include are log4j API and log4j core. Once you've got those in your project, then you should be able to use logging properly. Okay. All right. So the best practices, we kind of covered on these at the end, but I just wanted to make sure that I enumerate them specifically. Always use prepared statements. I showed you that XKCD comic that was alluding to the fact that the SQL injection attacks are one of the most common attack avenues against websites, and it's still the case, where you can inject SQL using, say, web forms or something like that. And if somebody is naively using string concatenation to do their prepared statements, that means that they are that allows you to arbitrarily execute any SQL that you put into your web form. So instead of putting your last name, you can put in last name and then drop database users or drop database students or something like that. Always make sure that you're using prepared statements, because all of those SQL statements will then be escaped out and it'll treat it as a string literal. If you want to take a look at an example in practice, make sure that you do the advanced activity in Lab 10. We take you through a typical SQL injection attack that is a specific type of attack called a cross-site scripting attack, where somebody can arbitrarily insert HTML code, say, and then have it re-rendered on the actual web page, giving a different result. Say, click here to actually log in, and it takes you to an external website. You can imagine the damage that you can do with that if you have not escaped HTML or you've not escaped SQL properly. The second one is do not use wildcards. It wastes resources. If you pull over 10 columns and you only end up using 2 of them, that means that you're pulling over 8 pieces of data times however many records over the wire, wasting bandwidth, slowing things down. Be more intentional. Make sure that you enumerate your columns, and when appropriate, use aliases to disambiguate. If you pull an actor ID from 2, right, you should say, I want that actor ID, and I'll call it actor ID with an alias, right? Finally, close your resources. Make sure that you are closing all of your result sets, prepared statements, and connections after you're done using them. There is one exception that we'll get to by the end of the day. That's part of the bonus lecture here today, where I'm going to show you how to do if we get to it, hopefully, rudimentary connection pooling. Okay. Don't store unencrypted sensitive data within your database, right? Passwords. When a database gets dumped, the first place you go to is password fields. And then you figure out what encryption technique they were using, what hash function they were using, and hopefully they were using a widely used one, and they didn't follow best practices, and you'll be able to use what are called rainbow tables to look things up, right? I demonstrated this morning just by finding, say, SHA-256 hash online, right? What is the most common password? Or what are, say, the 10,000 most common passwords? It's even a Wikipedia page that you can take a look at. Broken passwords, passwords that have been dumped or whatever, right? These are the 10,000 most common of them. And so you can say, like, freaks is one of the commonly used passwords. Actually, what is the most common password? What was number 1? Well, number 2, I guess, is password. Otherwise, it's just 1, 2, 3, 4, 5, 6, right? And if you hash this and store this hash in your database as your password, then guess what? Because that's so common, I was able to generate what's called a rainbow table. bunch of pre-computed password hashes, and all I have to do is a reverse lookup. Oh, okay, here is the password that was stored in the database. Okay, that corresponds to that password. I've now got access to your account, right? So even though it's being encrypted here, it's not being encrypted correctly with the best practices. What you really want to use is PBK, password-based key derivation function 2. PBK DF2 or something like that that incorporates what's called a salt, right? So instead of, say, a bad password like 12345 we'll go ahead and add in a salt like hello world, right? 2021, 22 is the year, right? This part here is called the salt, and it is not part of the password. Instead, what it is it's a string that you store in the database, right? And then you concatenate that, and then you hash that result. It's a little bit more sophisticated than that because you also actually rehash it tens of thousands of times to slow the work down, intentionally slow it down so that you can't generate these rainbow tables efficiently, right? So don't store unencrypted information. Use the best, even if you do, use the best practices like, say, password-based key derivation functions or something like that. Or better yet, the example I gave was Strava. It's a running app that I use. You can go ahead and let somebody else do it, right? Again, remember, what's the number of the answer that you should ask, or what's the first question you should ask yourself when solving a problem? Has somebody else already solved it for you, right? And so Google has solved it. Facebook has solved it. Apple has solved it, right? Let them do your security for you, right? And then, of course, now it's how good are they at security that becomes the question instead of how good are you at security, right? All right. Use a proper logging system. Again, log4j. We showed that on Thursday right before the break. And I showed it again to the main section if you want to watch that video. Anyway, let's go ahead and get rid of this. Right? I want to talk today a little bit about multi-threaded programming. It's just a really, really quick introduction. First of all, we need to define what concurrency is. Right? Or there are actually a couple of different ways of thinking about this. There's asynchronicity, which is the most basic way of thinking about this, where a task that does not block the remainder of the program, right? Or a task does not, I should say, block the remainder of a program, right? So, for example, to illustrate that, I'm just going to go to a typical website here, right? So if I click say hello, then this pops up and says hello, and I get rid of it, right? I can click on a drop-down menu, and I can select option A, and then option 0 is selected, option B, option 1 is selected, et cetera, right? Now what I'm going to do is I'm going to simulate a request to the website to say, load up more posts, or save this image, or something like that. And typically what you see in a website is something that looks like this, right? It's an asynchronous delay. Some busy thing is going on in the background. And to simulate that, I just put up that loading picture, right? I think it's like a 5-second delay or whatever it was, if you were counting it. But while that's working, it's not preventing me from doing anything else. It's going on in the background, asynchronously, right? I'll go ahead and do it again and show you that I can select things and even get results here without having to wait for that back end to come back with its answer of done, whatever it was doing. Right? That's an asynchronous delay, right? What does a busy delay look like? So if a busy delay, I click it and it freezes the entire app, right? I can't click on the drop-down menu. I can't click on the hello anymore until it gets done. At which point, all my clicks that I've been clicking, right? They all come right at once, right? You see that I clicked on the action here, and I also clicked on the hello, right? So, busy delay done. Which one is better? Asynchronous, right? If there's a busy task, it should be done in the background, and it should not block the remainder of the program. Right? Now, this is all written in JavaScript, which is single-threaded, so that's why it's called asynchronicity, concurrency, right? Oops, NC, there we go. But the whole idea is multiple things should be able to be done at the same time, concurrently, or in this case, asynchronously for this demonstration, right? For example, if you've got task 1, task 2, task 3, and task 4, and these were like lines of code or something like that, then you would expect that task 2, like if it was a C program or a Java program or whatever, that task 1 would have to fully execute and complete before you go on to the next line. Task 2 would have to fully execute and complete before you go on to the next line, right? Etc. That is single-threaded sequential programming. Asynchronicity is if you were to have, say, an asynchronous task. Task 1, task 2, those are synchronous. They have to complete before you go on to the next task. But task 3 here is asynchronous. What I do is I launch it off in the background, and it's functioning, right? It's going on, and I move on to task 4, right? So task 3 and task 4, they're happening in parallel, potentially in parallel, or one of them is in the background, or they're going back and forth, whatever. But think about it as them operating at the same time in parallel. Task 3 or task 4 could win, right? It could get done. It could get done with task 3, then 4, or it could get done with task 4 and then 3, right? It depends on what they're doing and how much computation time that they're taking, right? That's asynchronicity, which can be done with one thread, one processor, one program. What we're talking about is multithreading, excuse me, where we have multiple threads running independently of each other. They may be on one core. So for example, I'm on a Mac right now, and I've got, I think this is an i9, and I think I've got 8 cores. But because of hyper-threading, I can actually run 16 processes at the same time, I believe, right? And so I have essentially logical, I don't know how many logical cores, 8 logical cores, 16 virtual cores, whatever you want to call it. But it allows for scheduling. It allows, you have processes that may have to wait because they're depending on some certain piece of data. They might be waiting on I/O, et cetera, right? So we have multiple threads operating at the same time. You also have the concept of what's called parallel computing, where these multiple threads are all operating in parallel on the same machine, but on different processors, right? On different cores is the term we use. And then, of course, you can go even a step further, where you have distributed computing. Right? Distributed computing is where you have multiple programs, multiple processes running on completely physically different hardware. Right? For example, a cluster over in the HCC, the Holland Computing Center. Right? You could have 300 different actual machines with multiple cores on each or something like that. You could distribute your computing throughout the world. There was SETI at Home, I believe, is one of those examples of a massively distributed computing task. SETI at Home, right? The search for extraterrestrial life. If you sign up for it, you can allow them to you're allowing them to use your computer to do some data processing on deep space, data that's being collected. And this is a massively distributed computing process because people can opt in, they can opt out. So it's not just one piece of hardware. It's running on many millions of different pieces of hardware, all running different operating systems, different things all over the place. Right? That's distributed computing. The benefits, of course, hopefully are clear. Right? The efficiency immediately speeds up depending on how many cores you run it on. Right? That's not what I wanted. There we go. There. Suppose that a task took you 10 minutes. If you can split it up into 2 tasks that can run on 2 processors independently, then theoretically, you could have this process done in 5 minutes. Well, what's to stop you? What if if it took 10 minutes on one processor, what if you had 4 processors? Now it would take you 2.5 minutes, right? What if you had 80 processors or 10 processors, whatever, right? You can cut down the time divided by the number of processors that you're willing to farm it out to and work in parallel. At this point, I want to show you a demonstration. Now, this demonstration I used in the main section last semester. I don't know if I demonstrated this in the H section or not, but I've got a lot of demonstrations here. But let's just go ahead and look at count primes. Count primes threaded, okay? This is for C, all right? So don't worry about it. It uses POSIX threads. I just want to show you what it's doing and showing you the advantage of multi-threaded computing. What it's doing is it's creating these. Well, here, let me look. Let's look at a non-threaded version of this first, so that we can count the primes. We're just counting prime numbers from 2 up to some number n, right? How are we doing that? We're doing it through brute force. Given a number, to determine its prime, we simply try to divide it by every integer up to the square root of n, right? So that's not the way to do it. That's an exponential algorithm. I wanted an inefficient way of doing it so that it would be forced to do a lot of work, right? And what we do is we read in, command line arguments here, and then we print out the computational time and the total number of primes, okay? So gcc count primes .c, I need the square root function, there we go, a.out. So let's go up to like a million. 1, 2, 3, 1, 2, 3. How many prime numbers are there between 2 and 1 million? It only took a half a second, and it tells me that there are 78,498. Wolfram Alpha, tell me. Is that correct? Number of primes up to 1 million. I think I typed that correct. No, I did not. 10 million. That's 1 million. 78498. 78498. Excellent. Now, it was going from 2 up to a million, right? What if I went to 10 million? Took a half a second before. Since this is an exponential amount of work, this is going to take about 100 times as much, or no, not that much. I don't know. 10. What is it going to be? 40. It's way more, right? Exponentially more, right? I don't know. Hopefully that's still the answer, but whatever. Suppose that I wanted to go up to, this was what? How much? 10 million? 100 million. We're going to be sitting here for several minutes, probably, right? What if I split up my work? Instead of going from 2 up to 100 million, what if I split it up into 2 parts? 2 up to 500 million. What do I have here? 100 million? So 50 million. And then 50 million up to 100 million. Right? What if I split it up into 4 parts? Right? 0 up to 25 million, 25 million to 50 million, 50 million to 75 million, 75 million to 100 million. Right? What if I did it like that? And that's what this other program is doing. Let me go ahead and look at it. Count primes threaded. Okay. All it's doing is setting up a structure here for a range, low, say 50 million, up to 75 million, and then it reports the result in here. I also name this so that I can print it out and show you, thread XYZ reported this, right? And I've got the same isPrime function here, so it's still going to be using brute force. But we're going to split it up among multiple threads. In C, the way that you can create threads is through POSIX threads, P threads. So there's a P thread, and you can create them using, here I'm just allocating malloc here. But otherwise, you can create a thread. Where is it? Create thread. P thread create, right? I'm creating a bunch of threads here, however many you want. That's a command line argument. And then we join, in other words, we're going to wait. If we farm it out to 4 different threads, we want all of them to be done executing. Once they're done executing, we add up all of their results and report the grand total. Okay. So what this is doing, pthread join here, is it's waiting for all 4 of those to be done. Because if only 3 of them are done, right, and you're still waiting on this guy over here, you don't want to report a fractional result or an incomplete result. And then we report on how much time it took. Okay. So I'm going to go ahead and compile this. Count primes threaded. LM, and I have to compile it with the pthread library, so pthread, there we go, all right, and I'll run this. It requires that I put in the n, so what we were working with before, 1 million, and the number of threads. Well, if I just do it on 1 thread, it's going to be very comparable to what we did before with no threading at all, right, just a brute force, half a second about. But what if we did 1 million and 2 threads? Right? Then this should only be about 0.2 seconds or so. Right? Yep, about, right? Of course, it takes some time to build all of these threads. Let's go with 4. That should be about 0.1 or thereabouts, right? Oh, looks like no. Oh, sorry, that's actually the overall computation time, so it's actually adding them all up, right? Let's see. You know what? I think I commented out a line that I wanted. There, actual time, right? So computational time and actual time. So let's go ahead and recompile this, and let's rerun that for 1,000,004 threads. Right? There we go. Right? The actual time was not even calculable, right? It's essentially 0 seconds. But there's the total computation time, which is summing up all 4 of these threads. Each one of these threads acted for 0.1 seconds. And so summing them all up gave me 0.33 seconds or thereabouts. Right? Let's go ahead and pump it up to 10 million, but 1 thread. Right? So that 1 thread is searching from 0 up to 10 million now. And what was it before? Does anybody recall? Way up here. 10 million, 10 seconds here. Right? So we repeat that with 1 thread. What about 2 threads? How long should it take now? Approximately 5 seconds. Right? So now thread 1 and thread 2 are searching different ranges. There we go. So 5 seconds, 6 seconds, we're in the ballpark, right? What if I went up to 4? Should only take about 2.5 seconds now. Okay, a little bit higher, but we're getting lower, right? What if I pump it up all the way to however many there are on CSE? I am running on CSE right now. Does anybody know how many cores are on CSE? We can look it up. So CPU up, CPUs, how many? 64. Right? So let's try to grab all 64 processes, all 64 cores. We're probably not going to be lucky enough to get them all. There we go. Whoa. But it doesn't matter because the range is so small now that each thread gets done very, very, very quickly. Right? Let's pump this up to 1 billion. What is that? Is that a billion? 100 million. Right? All 64. There we go. All of the 64 are not running at the same time. But wow, 6 seconds. Right? If I had done that on 1 thread, how long do you think it would have taken for 100 million? Probably a half hour, maybe an hour or something like that. Right? Orders of magnitude greater because it's exponential. Right? So hopefully you see the benefits here immediately. In fact, let's go ahead and go with 64 and go up to 1 billion. I'm not going to, and then let's go ahead and run it in the background. Right? So htop. Oh, come on. There we go. There is all 64 processors of CSE running at 100% capacity right now. Oh, and now it died because I exceeded my CPU limit. Right? So I was running, it did kick me out eventually, right? If you are going to do something intensive like this, you need to do it on hardware where it's okay to do that, right? They've set limits on individual processes that, no, you can't take all 64 processors and cores and use them for 100% of the time for 24 hours, right? CSE would grind to a halt, right? So it kicked me out after a few seconds there, right? But let's go ahead and kick it down, I don't know, to maybe 16. Right? Oh, that's not what I want. Run it in the background so that I can actually view it. And now you see that only about 16, at any one time, any 16 processors, I'm grabbing them and running them at 100% of the capacity. So maybe some fans just kicked on in the basement over here in Avery, right? I don't know how long that's going to take, but we'll go ahead and leave it here and sit here and see how long it takes, okay? Anyway, hopefully you see that there is a benefit to efficiency here, but it does not come without a cost, right? There are lots of costs associated with this. First of all, it's not free, right? That we did not get a full speed up, right? It didn't go from 10 seconds down to exactly 5 seconds, 5 seconds down to exactly 2.5 seconds, because of course you are paying for the threads themselves, right? And all the work that goes into making the threads and maintaining the threads, etc. You also have problems of synchronization and race conditions. I solved that by making sure that each thread only worked on a particular portion of that range. What if I had created it so that two threads worked on overlapped, right? There was some overlap of work here, right? Then there would be a synchronization issue because, well, how many primes are between do we have in common? And we have to, resolve that. You also have synchronization issues of when one thread is reading, another thread shouldn't be writing and destroying the data that the first thread is working with. You have race conditions where you need one thread needs a particular resource and another thread needs a particular resource. They have a race condition to get to that resource and grab that resource and hold on to that resource. Ultimately, you might have starvation where this one poor little thread over here is waiting for those resources to execute and everybody just keeps grabbing them before you can get a chance, right? And that poor little thread starves and is never able to actually run or execute. And also, not every problem is parallelizable. There are problems that are inherently you cannot split up the work, right? We won't. From a practical perspective, there are other solutions, but it doesn't come out without the cost. Is the point, right? So I already demonstrated that in C. Let's demonstrate this in Java, right? Again, a process is an executing program with its own memory and resources. A thread, however, is different. A thread is within a process and can execute independent of other threads. Threads have their own context. What that means is that they have their own local memory, their own call stack, but they may share resources. For example, the program code itself is shared. Any heap memory may be shared by each thread, right? And the way that we can do this in Java is through a couple of things, right? There are several ways that Java supports multi-threaded programming. There is this object called a thread. That's what it says on the box there. It's a full thread implementation. There is also this interface called callable and this interface called runnable. The difference is that callable returns a result and blocks until it's done. A runnable does not return a result. Right? If you just have a task where you want to you set it off and it runs and it does its own thing, who cares? You free it. You free it to do its own thing, and it goes off and does its own thing. It never needs to report back. If you need to report back a result, then you need to use this callable interface. Right? Another way of doing this is with that one I'll primarily show you is with a future. So I have this number, say the number of primes between x and y. And I don't know what that number is, right? It could be 5, it could be 20. But in the future, I will need to know what that number is after I've computed that number. And that's what future does. It provides a future value. I don't know what it is. It runs at its own convenience. And if you ever ask it, well, what is your actual value? Give me the number. Actually, give me the number of primes between x and y. It says, okay, I'm not done computing yet. I'm going to block you. Right? You're going to go to sleep until I am done computing. And once I've got the result, I will wake you up and I will tell you the result. Okay? That's what I've implemented over here. Right? First of all, there's a brute force primes generator if you want. Otherwise, there's a callable setup here. I thought I did this with futures. Yeah, I did. Here we go. Here's the future. Right? It's a future result. Let's take a look at what it looks like. It's not gonna. Here's what runnable looks like. It implements runnable, and all it is this run function. And whatever you're going to do in your thread, you do it here. Right? It's not appropriate here because to get the result, you have to wait till it's done. Right? And so you would have to sit there and constantly busily asking it, are you done yet? Are you done yet? Are you done yet? No, I'm not. Are you done yet? No, I'm not. Are you done yet? Yes. Okay, now give me your result. And that's not really going to work with respect to what I want to do and count up the number of primes between a range. So I chose to implement this as a callable, right? And there is a call function here that provides a list of integers, all the primes, between a start and an end. So to set this up, what I've done is I've given the thread a name so that we can print it out and see the demonstration, the start and the end, and we create our primes list here. And it does when you call this thread, this runnable, it goes through all possibilities, and if it's prime, then it goes ahead and adds it to its list. Right? I've also got a toString method here that reports everything back. So how does this all work? Let me go ahead and show you the code. Right? Down here, I'm going with, what is this, 30 million? Yeah, this is 30 million. How many primes are there from 0 to or from 2 to 30 million? That's by default. Right? I made any changes? Whatever. There we go. And if we run this with one thread, it's going to take probably 10 seconds here on my computer. But while that's running, let's look and see what it looks like. Threads in Java are executed within this executor service or executor service. How would anybody pronounce that? Since it's an or, I'd say executor, right? Not executor, right? That's what that would pronounce. So I'm going to pronounce it executor service, right? It executes things, right? And so I create this new fixed thread pool. What a thread pool is it creates a bunch of threads, say 5 threads or 4 threads, let's make it even, right? And it puts them in this pool, and anybody who wants to can grab this thread and run a task on it. And that task will be this callable right here. It'll be calculating the number of primes between start and end. And so what I do is I break that up and create all these workers. I go from I times range size up to I plus 1 times range size. And then the last one, I'd go from, it's just the last range all the way up to, and not including n here, okay? And then I collect them all as futures. And then I'm timing myself here too. And what I do is I invoke all of those at the same time. And those will all start invoking, running independently. And down here, I actually ask for the results. Give me the size of your list of prime integers. Right? What that's going to do is it's going to block until that future value has actually been computed. Okay? And then I go through and print all the results, and I report the time and the total, etc. So there it is. Thread 0 found 1,857,859 primes. It went from 0 up to 300 million or 30 million. It took 17 seconds here. That was with one thread. What does it look like with 2 threads? How many seconds was it? About 15? Okay. So this should only be about 7 seconds. Why? Because I doubled the number of threads. Right? Hopefully go on. Okay, 10 seconds, thereabouts. I am running OBS right now, so that's taking a lot of processor time. In fact, it claims that it'll only take 7.7% of my CPU, but I doubt, right? Let's go ahead and fire it up for 4 threads. It was going a lot faster when I was in my office without OBS running. Right, now it's that's about a quarter of the original time now, right? Should I bother going up to 64 threads on my own computer? Probably not. I wonder how many threads I have available to me on my personal computer here. 16. Again, there's probably 8 cores, but hyperthreading makes it 16, I think. Don't quote me on that, right? So why would it be useless to go up to, well, let's go up to 16, right? And see how fast we can get this. Right? But, so 2.2 seconds. What if I double it again? It should be 1 second, right? Well, no, if I only have 16 cores, only 16 processes can run at any one time. It doesn't matter if you've got 128 threads, right? Only 16 of them can ever run at one time. And if you put your ear out really quick, or not quick, but carefully, what do you hear? My fan is going nuts right now. Why? Pop. Yep, there we go. So there are all my processes. There's OBS. Where's the rest of it? Oh, it's already done. Never mind, because I went up so high. But my fan is running, and so that's why I imagine there's a bunch of fans running down in the CSE library right now, or in the CSE the computing center. All right, up there. CPU time limit exceeded. So we never got a result. I've got these Java files on CSE, so let's see if we can get away with 64 processors there. Let's see. Oh, okay. I'm gonna have to go Java class path here. I think it's unl csc.multithreading multithread what is it called? Multithreaded, and then prime generator. Prime generator. And then we'll do it for 30 million, 1, 2, 3, 1, 2, 3, with say 4 processors. We won't get too greedy. Right? What was it over here? 2.2 seconds with, I think, 16 processors. Oh, wow. It's taking forever. Why? Okay, fine. 16, so let's go up to 8 processors. CSE is not all cracked up, not up to what it should be. There we go. I cut it in half. 16. Should only be, there we go, 4 seconds, right? Let's try to grab all of your, give me all your processors there. Oh wow, I was able to get them all. Right. Not all 64 were running at the same time. But now let's go ahead and kick it up. All right, I'm going to go ahead and kick this up and look at htop. Yeah. Now we're cooking. Look at all those processes that I'm running right there. CPU time limit exceeded. And then they all die. All right. Oh well. But anyway, that's the advantage of having multi-threaded programming, right? You can theoretically cut down the amount of work depending on how many processors you have. If you've got a lot of work, throw more hardware at it, right? Purchase more hardware. Have entire clusters of hardware. Outsource it to, say, Amazon Web Services, where they have millions of cores available to you, right? And you can do some really, really fantastic computationally intensive work in a fraction of the time, right? Where that fraction is you're paying for additional hardware, right? Okay. Let's translate that into, say, something that we could use for our not necessarily for your project, but something that you could use in general in a web a database-backed application, connection pool. Right? So remember that, and I wish I hadn't closed it yet. Remember that we had this thing called a thread pool. So what is a pool? First of all, it is a collection of shared resources. Right? Go to the library. You can check out a book, right? Read that book, use that book as a resource. What do you do when you're done using that book? Yeah, you return it. You don't throw it in the trash, right? With respect to, say, database connections, making that connection is actually the most expensive thing that you can do. So what I want to do is I want to create a connection pool. A pool of connections that I open up. Say I open up 10 connections. I put this in this pool. And your app, instead of making its own connections and closing its own connections over and over and over again, it simply checks it out like a library book. When it's done using it, it doesn't close it. It puts it back in the pool so that another thread could use it. Now, everything that we've done up to this point is just single-threaded. But you can imagine this running in a much larger application where you've got many different workers, many different, say, web requests coming in, and you have to service all these requests, and they're all asynchronous, and they're all independent, and they're all on their own threads. Right? How do we support that? Right? Well, first of all, I need a way to store all those connections. So here's my first idea. Right? Public static list of connection, right? Connections, right? Is equal to new array list of connections. I'm going to have to import all of these, of course. List, array list, and connection. I want a java.sql connection. Where were we? Let's go back over here to, nope, not that. Game data loader. What was my, there we go. I store these things, say, over here in the connection pool. These are all private static final variables. There we go. Right. And to set up this connection pool, first of all, I've already created the pool itself here. But now let's go ahead and go into a static block. Right. There are better ways of doing this. I would use a what's called a singleton pattern here, but I don't have time to go through that. So I'll just go ahead and set this up as static connections. And let's go ahead and say that we want, I don't know, public static final num connections. And we'll say 10, right? And what I'm going to do is I'm going to go into a for loop here for int I equals 0, I is less than num connections. Thank you. Int, there we go. Or a var. Oh, I can't do that? Why not? Var, why is var not allowed here? Only local variables? Var foo is equal to 10. Okay. Apparently static final variables cannot be inferred even though I'm assigning it right there. Again, don't use var. That's stupid. Right? All right, so I'm going to go ahead and create a new connection here, which means I'm going to do this in one big try catch, right? And I'm just going to steal the code, actually, for creating a connection. There we go. And I will connection con is equal to this, and once I've got that, I will just add it to the pool. In fact, I'll call it pool, right? Pool.add con. There we go. Otherwise, could not get connection. Fine, whatever. Right? I did the try out there, so let's move the catch down here. There we go. Okay, and reformat. So there's my setup. I'm just going to open up 10 connections and put them into this pool. Now, instead of actually opening up your own connection, what would it look like? Public static connection, get connection. This dot pool dot remove dot. Okay, what's wrong? Oh, not this. Pool. I shouldn't have called it pool. That confused myself. I should call it pool, all uppercase. Why? Because it is a static variable. There we go. Pool dot, what is it? Remove the element at the specified position and returns it, I believe. 0 and return this. There we go. So I'm removing it from the pool and immediately returning it back to whoever asked for it. The opposite operation, we don't close it, we simply put it back into the pool. Static void get connection, give connection. I really don't like that. So you check out a library book, you check in. What should we call this? You're giving the connection back. Yeah, well, I don't think you could. That's a key word. Return connection. Okay. Yeah, because you're returning it. I don't like that either. Give back connection. Put connection. There we go. Opposite of get. All right. Pool dot add con. So do you see what I'm doing here? I'm removing the first one, and then when I put it back, I'm putting it back over here. Right? So if I've got 4 connections, this gets checked out, and when it gets checked in, it gets put back at the end of the line. Why? What if I was always removing the first and putting it right back? Removing the first, putting it right back? Yeah, the guys at the end, they never get used, right? By putting these in a line and taking from the front of the line and going to the back of the line, I'm ensuring that everybody gets, all these connections get used equally, right? Roughly, okay? So what does that look like over here in Game Data Loader? Now you don't need this connection anymore. Instead, if you want a connection, con is equal to connection pool dot get connection, right? Dot, 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 dot. And instead of closing it, do not close it. Instead, connection pool dot return. Now I've put connection con. There we go. Give it back. Right? Now let's am I actually using this game data loader, get all platforms. I want to make sure that this actually works. Darn it. Get all platforms. Oh yeah, because it does load up. So let's just go ahead and run this, and it's guaranteed to actually run here. There we go. And so you saw that it was completely opaque, right? We were not aware that one of those functions was actually using connection pooling, and another of those functions was not, right? Much better solution here. What happens when we get greedy and try to open up 40 connections? Remember how many we were limited to? I think 30. Yeah, and so when we try, you already have max user connections, active connections, so it's not going to let us do that. All right, don't get greedy. Let's kick it back down to 10, right? Just as with threads, don't get greedy, otherwise the CSE is going to kill your program and say CPU time limit exceeded. Also, I mean, if I only have 30 connections, there's no reason to open up more, right? Open up a sensible number of connections and then reuse them. There is a big problem here, though, right? This only works right now because it's a very simple example, right? And let's see, it works. Yep, okay, everything was reset. Think about this in terms of multi-threaded programming. What if I've got, say, 11 threads, or let's go with 15 threads, right? 15 threads. Now, the first 10 of them, they grab all the connections, and there are no more connections to add. Let's simulate that by saying that we don't create any connections here. Is there a connection to give you? Nope. So what's going to end up happening? Index out of bounds exception here. Right? There were no connections. There were no connections left. The first 10 threads got the first 10 connections. The last 5 threads are going to error out because they can't get any connections. So we need to use something that is thread safe. Lists are not thread safe, but a blocking queue is. Right? Let's go ahead and import this. And I think that there's an array blocking queue. There we go. Let's kick this back up to 10. Num connections. There we go. And import that. There we go. So I likened that idea of taking out a connection and then putting it back at the end of the line as a line. What's another name for a line? A queue. Right? And that's what this blocking queue is doing. But instead of when it's empty, there are none left to give you. What it does is it doesn't say remove anymore. I have to change these as well. But instead it says, hold on, wait, there are no more connections to give. Block, right? Go to sleep and wait your turn until a connection becomes available. I'll wake you up and here's your connection, right? Instead of just dying, right? Now, of course, we do have to remove, like, pool dot, what is it? Pull? Yeah, pull. That does it from the front, I believe. Removes the head of the queue, and then this adds to the tail of the queue. I think it should be offer. I think you can use add, but offer is a little bit better. Pull and offer are the pull things out, not pull, P-U-L-L, but pull like, are you there? Are you there yet? Are you there yet? Are you there yet? You're pulling it and pulling it out. Offering it is offering it back to the pool, right? And now this one will work, right? Because we do have 10 connections here, but I'll simulate running out of connections here, and at this point it'll just hang. Or really? What? It should not hang. Illegal argument exception. Oh, I can't even create it now. Fine. I'll make that 10, but I'll make that 0. All right, so I never actually create any connections. There. Now it should just hang, but it doesn't. Why? Because con is null. Okay. Now it should be... blocking queue. There's probably something else that I have to do. Not pull and offer, maybe. But what is thread safe? Which one's the thread safe one? Here. Consume and put. There we go. I think. So put and consume. Which one was which? No, queue.take. Dang it. That's a producer-consumer pattern. Oh, here, block. Put and take. That's what I want. Put and take, because they block. Right. Let me zoom in for you. There we go. Put and take, not the other ones. So if I want to put and take, there we go. And I'm going to have to surround these with, come on. That's not what I want. I'm going to have to surround them with try catches for interrupted exceptions. Surround with the try catch. There we go. Surround with the try catch. There we go. There. Now, come on. Return null. That should be considered dead code though, because if that if it fails to return here, that means it was through an exception and it would never get to this point. But there, I'm satisfying the compiler right now. There we go. Finally. So what is it doing? It's sitting there. There were 0 connections created because of the way that I did it up here, right? Right there. And so it asked for a connection, and the pool said, okay, wait your turn. There's no connections available. Block. And what do I have here? Not an infinite loop, kind of an infinite pull loop, but it's no connections ever become available, and therefore it blocks forever. Right. Let me go ahead and stop and terminate the process now. Fix it back up to 10, so num connections. Right. And now everything works. And this is a basic, really quick connection pooling solution. Right. Now, if you wanted to do this in real life, you would pull in a library to do it, because it's going to give you a hell of a lot more bells and whistles, and way more than I just did, right? But blocking queue is what you want, because again, if you have 10 connections and they're all checked out, you want to be able to block other threads from accessing it. You don't want those threads to just die. Right? I don't know. I don't know why only 3 people. YouTube questions. Right? I think most people watch recordings, hopefully, or maybe they just ignore them all. Right? All right, so questions on multi-threaded computing? I gave you the basic ideas. I did not give you the enough maybe to go off and start doing it on your own, but I gave you enough to contemplate going off and playing around with stuff. Whenever I do this, I can never think of a good solution, like a real-world solution to do this on. So I always have to make up some, prime number generator or something like that. If anybody has any good, well, the other examples I've got, what I have here, Imager, before they shut down the URL, downloading a bunch of images. There we go. All right, there's my old client key. So Imager is a image sharing website, and you could and if you can go ahead and download a whole bunch of images, download these 50 images that this person has posted, and then save them to disk. Well, if you did that with one thread, you download image 1, then download image 2, then 3, then 4, then 5. But if you did this all in threads, what you could do is you could launch 16 threads and download 16 images in parallel. Right? That was another one. Password cracking. You can farm it out based on dictionary results, and a couple of other toy examples. But the whole idea with multi-threaded programming is that you can get a lot done very quickly, but at the same time, and this is the things that I'm not covering here, that would be like 1 or 2 or maybe even 3 classes to cover the solutions to all of these things. If you just use an API like, say, a blocking queue, or the future that I showed you, right? The future stuff, list of futures, lists of integers, right? If you just use an API, it's all taken care of for you. But understanding everything that's going on under the hood is at least 2 or 3 other classes. All right, so that's one of the, I guess this is the second extra lecture that we do in H. We might do one or two more, depending on where we get. Otherwise, on Thursday, we will cover some just a wrap-up of the first half of the course by talking about multi-tier architecture. And then that will mark the halfway point of the course, after which we get into data structures and algorithms. So lists and list-based data structures like queues, right? A queue is a list-based data structure. Linked lists, array-based lists, stacks, and then we'll get into algorithms, algorithm analysis, and then we will get into tree-based data structures. And that will round out the rest of this semester. 6 weeks left. Everything that we've covered up to today takes you through phase 5. Right. So if you wanted to, you could get all the way done through phase 5 at this point. Right. Any questions? No questions online, it looks like. Nope. All right. Then have a good day.